Hi, we're about to talk about quantum entanglement. We want to know about quantum entanglement because it is known as the heart of quantum physics. This topic gave us the insights about the fundamental principles of the physics world, and at the same time, it gave us the basics of knowledge protocols that allows efficient communication and it takes computer science capacities far more than its classic counterparts. In order to better understand quantum entanglement, we have to be familiar with the terms object permanence and realism. That explains that the universe exists independently of the observer's mind, and quantum entanglement even rejects this basic premise. It was then created the Bohr-Einstein debate, where the first one said that it was meaningless to assign reality to the universe in the absence of observation, and that in the intervals between measurements, quantum systems truly exist as a mixture of all possible properties, and as we know, that is the superposition of states. On the other hand, Einstein insisted in an objective reality that was independent of our observation of it. He said that there must be local hidden variables that reflect a more physical underlying reality. Together with Podolsky and Rosen, they proposed a quantum scenario, where apart from abandoning the idea of realism, they also abandoned the term locality. And that's where they introduced the EPR paradox, which we will talk about later. Quantum entanglement can be explained with two particles. They interact with each other and they influence each other in a way that their properties are connected. We call them an entangled pair. But to preserve quantum uncertainty, we do not measure its properties. Quantum mechanics forces us to describe this combination with a single wave function that encompasses all of possible states of, of the particles. This was the continuity of the Bohr-Einstein debate, where they were trying to explain how this entanglement pair behaves and how it affects reality.
Now, let's imagine that we have a quantum system with angular momentum equal to 0. Then this system emits two photons at the same time. Because the angular momentum must be kept, if one of the photons has a spin up, the other should have a spin down. At the same time, so they cancel and they have an angular momentum equal to 0. These two photons are correlated by a wave function, and also they are following the superposition principle that says that the two photons will have a spin up and down at the same time. Now, let's say that I measure one of the photons. I take them galaxies apart, and it turns out that it has a spin up. Then, because of superposition, the other must have a spin down, so the momentum cancels. But how can this information travel so fast throughout the function? Because superposition then would be crashed. So it would mean also that the information travels faster than light. And according to Einstein and the postulates on special relativity, nothing can travel faster than light. So then Einstein, Podolsky, and Rosen theorized this paradox, also known as the EPR paradox, and said that the information was predetermined from the creation of every photon. And this information was also hidden in each photon, so they would know what spin to take without the communication between them. They called this hidden information as local hidden variables. Almost 30 years later, a scientist called Johannes Bell came and he proved that there was no hidden information. He made a theorem called Bell's theorem, but we'll talk about that later.
At the time that the article by Einstein, Podolsky, and Rosen was published, it caused quite a stir in all those who defend the theory of quantum mechanics, since the document questioned whether the quantum mechanical description of physical reality is considered complete, to which Einstein replied that no. And so this article, he was taking quantum mechanics to an absurd, to an paradox that my partner Alondra has previously explained. Within this paradox, something arises that Einstein called the spooky action at distance, already known as quantum entanglement, and this occurs when a pair of growth or particle interact in such a way that the behavior of one determines the behavior of the other. For example, if one of the tangled particles changes its shape simultaneously, doesn't matter the distance between them, whether it is a few meters or many galaxies, immediately, that is in time zero, the particles finds out. Einstein said that it was not possible since the information between the two particles was traveling at a speed faster than the speed of light. And back then, thanks to relativity, it was known that nothing can travel at a speed higher than the speed of light. So, how could the second particle be informed instantaneously and the distance of the fact? Justified Einstein said that the particles in question, from their origin, should have been predisposed in this way and then be measured by humans and not the other way around.
Now, I want to introduce the concept of Bell's theorem, also known as Bell's inequality. This theorem proves that quantum physics is incompatible with the local hidden variable theories. In 1935, physicists Albert Einstein, Boris Podolsky, and Nathan Rosen proposed that quantum particles must carry some physical property or attribute not present in quantum theory. And the uncertainties that we now know are due to the probabilistic nature of the quantum world are a result of the ignorance of these attributes, later called hidden variable. Now let's imagine we have a source of light in the middle of a room. Then every minute, on the minute, it sends out two photons in opposite directions. On the left and on the right of the source, there are two identical boxes that are designed to receive the photons. Each box has a light on it. Every minute as the photon hits the box, the light will flash either red or green. From then, minute to minute, the color of the light seems quite random. Sometimes it's red, sometimes it's green, with no clear pattern one way or another. If you stick your hand in the path of the photon, the light bulb just doesn't flash. It seems that this box is detecting some property of the photon. However, due to the fact that these protons are generated at the same time by the same source, they are entangled. So, other physicists like Einstein, Podolsky, and Rosen said that because they're created at the same time by the same source and they're entangled, then they must have an attribute or a characteristic in common, and that characteristic is what the box is reading. If this characteristic is 1, then the box will turn red, and if it's 0, then it will turn green. Now, let's think of this experiment another way. You have two boxes, and in each box, you have 3 doors. So now instead of just going directly into the box and using a light, you have to choose to open one of the 3 doors. Now, if you open the same door in both boxes, say door 1 and door 1, then you will get the same color, either red or green. However, when you try to do it seemingly at random, say in the right you choose box number 2, and in the left you choose box number 1, door number 1, then while doing it in paper, you realize that you should have about 55.5% of probabilities of getting the same color when you open the doors at random. Because each door that's different has a 50-50, but the doors that are the same, which is 1 to 1, 2 to 2, and 3 to 3, have 100% probability of getting the same color. So when you do all the math, you will get a 55.5% probability of getting the same door. When you actually do the experiment in a controlled environment, in a lab, with proper tools, not just your imagination, you will see that the quantum mechanics predictions will come true, which is 50-50. It doesn't matter what door you open, it doesn't matter how random it seems, when you average all of your results, you will always get a 50-50. And this is what proves that there is no hidden variable, there is no intrinsic property that these particles have that the machine is reading. You really just don't know. You don't know why it's red and you don't know why it's green, it just happens. And as complicated as this is to imagine, it's one of the core principles of quantum physics, the uncertainty. And to date, these types of experiments, called Bell tests, have found that the hypothesis of local hidden variables is just inconsistent with the way that the physical systems do in fact behave. And while the significance of this theorem is not in doubt, its full implications for the interpretation of quantum mechanics and our general knowledge and understanding of physics remains unresolved.
Now the question is, how do we link up to quantum particles? Well, in this case we're going to be talking about the Cooper pair. The Cooper pair is a pair of electrons that are in a superconductor. In this method, we try to separate those electrons of the superconductor with a set that is a single electron transistor. These transistors just allow one electron to pass. It can be putting the electron in the superconductor or taking it out. So the first step is to put the set, the single electron transistor, in one side of the metal, the superconductor. Superconductors don't like free electrons. What's gonna happen is that the superconductor is gonna send the other free electron of the same S shell to the other side of the superconductor. Then we put another set, another single electron transistor, and with this we're gonna separate them, and we're gonna separate them like kilometers away. And here the question is, how many kilometers can the electrons like remain entangled once they are separated? And the question is that the limit we have today is 1200 meters. But wait, don't think that this happens just like that. Actually, the success rate is about 20%, and actually 5 years ago when they started to make this process it was about 3%, so it takes a lot of time. And now let's see some applications. There are two applications, both have to do with information, and here's the thing. In order for us not to destroy Bell equations, information cannot be transmitted because information has energy, and energy cannot be transmitted instantaneously as these changes between electrons happen. So there is a lot of investigation trying to find out how to make this possible. The other application is quantum computers. This one is possible. In this one, what they are trying to create is quantum qubits. That's why they are called qubits, because it's quantum bits, actually quantum bits. And what we use here is the probability of the electrons to be in different states, and not like in the modern computers, not so modern if we take into account that we're gonna have quantum computers. What happens is that in modern computers there are just two possible states, 0 or 1, that is on and off. But with quantum bits we are able to have those, but also they're going to be in superposition, so you can process everything you do with a normal computer, but with half of time you require.